Hello students, today I am going to discuss about one of the experiments, that is calculation of thermodynamic functions from electromotive force measurements of zinc copper system that is being taken as an example here. So before going to the experiment, I want to give a gist of what you have learned from the previous classes. So we have to know about what is electrode potential, what is an electrochemical cell, and what is an anode, what is a cathode, and then what kind of reactions happen there. So when it comes to the electrode potential, that means that it is a measurement of the tendency of a metal, whether it is going to lose the electrons or gain the electrons in the presence of the solution of its own salt. And the electrochemical cells are known for the conversion of chemical energy into electric energy through a redox reaction. So the anode and cathode here, we are going to have two different metal systems. For the zinc copper, zinc will act as the anode and copper will act as cathode. So when it comes to the zinc copper system, we can see that the EMF values can be measured by a potentiometer, and then the EMFs depend on two factors, that is temperature and the concentration of the electrolyte solution. So the observations of this Daniell cell or galvanic cell are oxidation of zinc metal and reduction of copper 2+ ions to copper metal, and then production of heat energy. So when it comes to the experiment here, you can see that we have taken a zinc rod that is immersed in the zinc salt solution. This is called half cell, and then you see that in another beaker we have taken copper metal rod that is immersed in the copper salt solution. So when we combine them together through a voltmeter, you can see that the cell is now complete. So now what happens here, the zinc rod here, it acts as an anode and oxidation happens here. So zinc metal, it will be converted into zinc 2+ ions and then 2 electrons. So then what happens here, the other side, the copper metal rod that is immersed in the copper sulfate solution, then the copper 2+ ions, they'll take the electrons that released from the zinc rod and then they'll be reduced to the copper metal, and you see that copper metal will be coated on the surface of the electrode. So this reaction always, this redox reaction always produces heat energy. So these are the three different observations that we can see prominently from this. You can see the construction of a Daniell cell here. So the zinc rod is immersed in the zinc nitrate solution and the copper rod is immersed in the copper nitrate solution, and these two are connected to a voltmeter, and the salt wedge is given here for the movement of cations and anions to the respective positions. So when it comes to the thermodynamic functions, so what is the importance of them? So you see that we have three different types of thermodynamic functions that we are going to look into. So number one is change in the Gibbs free energy, that is the capacity of the system to do the work. So that means that the spontaneity of the chemical reaction can be seen, whether it is thermodynamically feasible or not. And the second one, change in the enthalpy, that you can see that the heat of the reaction of a chemical process can be measured. Of course, this can also give the other information about whether the reaction is endothermic or exothermic. And when it comes to the third one, change in the entropy, that is a thermal energy per unit temperature that is unavailable for doing the useful work in the system. The physical significance of the delta S can be, that is a randomness in the system or degree of the randomness. So in this Daniell cell, so what we are going to do is we are going to immerse the metal electrodes, zinc electrode in zinc salt solution and copper metal in copper salt solution. Thereby we are going to record the EMF value. So this is an experimental value. So then we are going to calculate the EMF value at the E cell values through Nennes equation. So then what happens here, from the values that we receive, we are going to calculate the change in the free energy and change in the enthalpy and then change in the entropy. So then now directly we can see that the free energy change is equal to minus NFE. So N and F are constants here. So Faraday's constant, F is equal to Faraday's constant, N is equal to number of electrons transferred in the reaction, and then E is the E cell potential. So then what happens here, if the delta G is negative, that means that the reaction is spontaneous. So that means that the EMF value must be positive. Then Further, we can also use this expression for the free energy, that is delta G is equal to delta H minus T del S. So, or maybe delta H is equal to delta G plus T delta S. So, if the delta S values are known, we can directly get the delta H values from this expression. Otherwise, then if the delta S values are not known, then what we can do is we can use the Gibbs-Helmholtz equation. So, that is delta H is equal to delta G minus T into d of delta G by dt at constant pressure. So, from this we can calculate the delta H values, and then once we get now we have the delta G value and we have the delta H value, then now you see that we can calculate the delta S from the delta H is equal to delta G from T delta S expression. So, then you see that from this delta S is equal to delta H minus delta G by T. So, from this now we calculate these thermodynamic functions for all the concentrations that we use and also at different temperatures. So, now the final result that appears here is that we are going to have 3 different concentrations and we are going to take at 40 degree centigrade temperature, and then you see that we are going to have the E cell value and delta G, delta H and delta S values. Whatever the results that we calculate, we are going to put them there and we are going to compare the results, and whether the reaction is spontaneous or not, whether the reaction is thermodynamically, endothermic or exothermic, and we can also see that how much amount that was not used in the reaction. Now we are coming to the experimental section where we are going to use a digital potentiometer, and this particular experiment has 2 parts. The first part is we are going to measure the single electrode potentials of zinc and copper electrodes, dipped in their respective salt solutions with respect to the calomel electrode. So, here calomel electrode is a reference electrode. With respect to that, we are going to measure the EMF of the zinc and copper systems. So, in the second part, we are going to put the zinc and copper systems together, and we are going to make a Daniell cell, and then we are going to from that we are going to record the EMF values, and then further we are going to go for the other thermodynamic functions. Okay. So, now here, so what happens, we are going to have the calomel electrode here, and this is dipped in the saturated potassium chloride solution, and then I am just connecting this to the the terminal here, the black terminal, and then I am going to record the single electrode potential of copper system here, and this is the copper electrode, and then we are going to have the copper solution. This is a 0.1 molar solution, and then we are going to dip this into the copper electrode is now dipped into the copper sulfate solution, and then I am connecting the terminal here, and then you can see that here we are going to combine these 2 half cells. Now you see that we are going to put them together through a salt bridge, and the salt bridge role is here that it is going to facilitate the mobility of the ions and thereby to maintain the electron neutrality. So, what happens here, once we get this, now the potentiometer, you can see the reading is going to be 0.024. So, this is the potential for the copper system with respect to the calomel electrode. So, in a similar way, we can measure 2 other concentrations of copper, that is 0.01 and 0.05 molar concentrations. Thereby, we will be able to record the EMF values, and then so from that we will be able to calculate the E cell values. Now we are going to move to the zinc system, where now you can see that the calomel electrode dipped in the potassium chloride solution, saturated potassium chloride solution is connected to the potentiometer, and now I am going to take one of the concentrations of the zinc, that is 0.1 normal, and then I am going to dip the zinc electrode here in 0.1 normal solution, and now I am going to connect to the potentiometer. You can see that, and now I am going to put them together through a salt bridge. So, then immediately you can see the appearance of the potential here. So, it is going to be in the negative values. You can see that, so it is going to be minus 0.962 volts. So, now this is the one now for the 0.1 normal zinc solution that is dipped with the zinc electrode. So, single electrode potential of zinc, And then in a similar way, we can also calculate, we can also get the EMF values for the other two concentrations 0.01 and 0.05 normal zinc salt solutions. Now after that, so we are going to put these results in the table form, and then we are going to use the Nernst equation to make the complete cell reaction here. So with respect to the calomel electrode as a kind of reference electrode. Now we are going to come to the construction of a Daniell cell. So using that zinc system and copper system, we are going to put them together, and then we have connected them to the potentiometer. Now you can see the value that is shown here. So here we have used 0.1 normal concentration of zinc sulfate and 0.1 normal concentration of copper sulfate, and both were connected here. You can see that with the salt bridge. So actually the standard potential it should be around plus 1.1 volts. So now here the value is is close to that plus 1.021. So now this is at room temperature. We have conducted this experiment, and you see that the Daniell cell now it shows the EMF value plus 1.021, and now we are doing the other experiments like using different concentration of zinc and copper, and so 0.05 copper as it was shown in the final result. You can see that 0.1 normal zinc and 0.05 normal copper, as well as 0.05 copper solution and 0.1 normal zinc sulfate solution. So then we are going to record the EMF values, and using these EMF values we are going to these are all experimentally obtained. Now we are going to use a Nernst equation to get the E cell, complete E cell potentials, and then we are going to use them for the the change in the Gibbs free energy expressions. Then further we are going to calculate the other thermodynamic functions. So just now we have seen we have measured the EMF of the zinc and copper system, this Daniell cell at room temperature. Now we are checking at the slightly higher temperature, that is at 50 degrees. Now we can see that the potential is slightly there is a slight increase in the potential value, that is 1.036 volts. So like this we are going to measure the EMF values of this Daniell cell at different concentrations of zinc and copper. Now we are coming to the calculations. This is an example here. So we have taken the concentration of zinc as 0.05 molar, and the concentration of copper is taken as 0.01 molar. So we can see that how we are substituting them in the Nernst equation, and then we have the constant values given here, and we will be able to get the E cell potential. After getting the E cell values, we can substitute those values in the expression here. So where delta G is equal to minus NEF or minus NFE. So using these constant values, we will be able to get the delta G value, the change in the free energy, and this can be used even further concentrations as well as different temperature E cell values. So now we are going to have two different temperatures here. So the first one we have done at room temperature, that is 30 degrees centigrade temperature, and the second one is at 50 degrees centigrade temperature. So for the delta H calculation, we need to take the average of this. So for that, so we are going to have the values for 40 degrees centigrade temperature. So we are going to get the average of delta G for both the temperatures, and then we are going to calculate we are going to use this for the Gibbs-Helmholtz equation. So for example, we have given here, so delta G is equal to delta H plus T into d of delta G by d of T at constant pressure. So these delta G values are given here and with respect to temperatures, and now we will be able to get the delta H values, and so from this we will be able to calculate the delta S using the expression delta G is equal to delta H minus T delta S. So we will be able to calculate the delta S. So now you see that here the final table, it tells us so what we have learned from the experiment. Number one, so we are going to look at the construction of a Daniell cell, and so we know so how the EMF value will be influenced by the temperature and concentration. So number 3, we'll be able to calculate the thermodynamic functions like change in the free energy, change in the enthalpy and change in the entropy.